Okay, good morning, everybody. We're going to learn about GPU computing in Python today. It's a good thing we're not learning about something boring like CPU computing that would put you straight to sleep. We're going to learn about GPU computing, which is going to wake you up better than your coffee. Okay, so we're using the same repository as yesterday, which is linked from the LSST-DSFP session 21 repo. It's the L. Garrison repository. I think everybody has cloned that from yesterday, but we're actually not going to be running code today on your laptops because most of your laptops will not have an NVIDIA GPU. So instead, you're going to go to GitHub and you click on the link to open the Colab notebook for Lecture X, GPU Accelerated Python with CuPy and NumPy. So it's the third Colab link in the L. Garrison repository for this session. Okay, I'm going to give everybody a second to find this page, find this link. And I encourage you to follow along with the lecture, run things as I'm running them. Raise your hand and ask questions, and we can try new things that aren't in the lecture. And then for the problems that you'll also be using Colab. Okay, once you've found the Colab link, in the notebook, there's an important thing to do. And I'm going to switch to my work account here. There's one more important thing that you need to do when you open this notebook, and that's click on this arrow where my mouse is on the right-hand side of the screen next to the connect button. So I'm not going to click connect yet. I'm going to click the little down arrow and click change runtime type because we need to ask Colab for a GPU. So you should find this screen where it gives you the different hardware accelerators, and you're going to select T4 GPU. And then click save in the bottom right. Okay, raise your hand if you haven't found the screen yet. Need me to show that again? Okay, great. Now I'm going to click connect. That's fine. Cool. Okay, and I'm going to scroll down for myself. It's going to say the notebook is not authored by Google. That's right, because I'm not Google. And then we're going to just run the first few cells. Okay, great. So the first few cells run, so it seems like we have a CUDA-connected notebook here. Okay, GPU computing in Python. What are GPUs, first of all? And I'm going to start by talking about what CPUs are. And CPUs are the most common type of processor in your laptop or on a compute node in your cluster. By default, everything runs on the CPU. When you go to the command line, you type Python, import NumPy, create some NumPy array. All of that is happening on your CPU. That's the main processor that everything runs on. And when you make an array allocation with NumPy, that allocation is living in the CPU's memory, which we usually just call RAM. A graphics processing unit is a special type of processor that has its own memory and specializes in highly parallel calculations. We usually call it a coprocessor because it runs alongside the CPU. It has its own memory, its own compute cores. So running things on the GPU, we say to run things on the GPU, we offload them from the CPU. So the CPU isn't doing that work. We're passing it off to the GPU. It does that offloaded computation, and then we fetch the result back to the CPU. In order to actually print or do anything with the result from the GPU, we have to transfer the memory back from the GPU to the CPU. So it requires a little bit more legwork on the part of the programmer in terms of managing what memory is living in the CPU, what memory is living in the GPU, but we'll see some examples of that. You may know that GPUs started out as specialized devices for accelerating 3D graphics rendering, mostly for video games, because the problem of processing millions of pixels on a screen in parallel is a highly parallel computation. And so specialized processors were used to give gamers the frame rate that they wanted. And it turns out that this highly parallel processing paradigm is really useful for a lot of applications in scientific computing, like matrix multiplication, where you're just doing the same like multiplications and additions just on different parts of the array, but it's all fundamentally the same operations being executed in parallel. So the first examples of GPU programming were actually using graphics libraries and sort of smuggling in numerical algorithms as graphics computations. Today, we don't have to do that. We use dedicated GPU programming languages. We usually use CUDA, as I have written here somewhere. CUDA is NVIDIA's GPU programming language, and NVIDIA makes most GPUs that are used in high-performance computing. So we're just going to be learning about that today. OK. Oh, Colab doesn't want to show my image. That's OK. I will show it here. We'll get to that in just a second. OK, so I just wanted to put a picture to this idea that I started talking about already, which is that GPUs are highly parallel processors. Oh, and I'm going to change this to light mode so you can see the labels down at the bottom. On the left, I'm showing a very highly schematic view of a CPU, and on the right, I'm showing a schematic view of a GPU. This CPU has 4 computing cores, shown in green. Each of them has their own level 1 cache, a little bit of fast memory, and has their own control module, meaning, which just here means that each of these cores can execute its own stream of computations independent of any other core. And then they might share some larger, slower level 2 cache, likewise for level 3, all the way to DRAM or RAM, as we just usually call it. Now, the GPU, on the other hand, has way more cores than a CPU, but the cores don't operate independently. What's being shown here is that each row of these cores shares one control unit in yellow. So these cores operate in lockstep. They can operate on different pieces of data, but if one core in this row is doing a multiplication, they all have to be doing a multiplication. If one is doing an addition, they all have to be doing an addition. So GPUs are less flexible in terms of doing individual computations or things like taking if statements. One core can't take a different branch of an if statement from another core. But if you have a problem where you can have a lot of cores doing the same operations, then you can get a massive speed up over the CPU. And you can read more about this in gory detail in the NVIDIA C programming guide, which I've linked. And just to sort of break down what I've already been telling you, sort of comparing some of the overarching characteristics of CPUs and GPUs in this table, where CPUs are general purpose, and the individual cores have a lot of flexibility. GPUs are very specialized to highly parallel computations. CPUs also typically have much higher per core clock speeds, and GPUs have lower clock speeds, but just many more cores, and that's how they gain their performance advantage. And this can be thousands of cores, whereas CPUs can usually have a few dozen. CPUs are sort of the default place where programs run, whereas GPUs, you have to program for them specifically. We're going to use CUDA. GPUs have less memory than CPUs, but the memory bandwidth is better, but the total compute rate, which I'm calling T-flops here, or trillions of floating point operations per second, can be much higher than the CPU. And also, one characteristic that's a little bit underappreciated about GPUs, but is maybe the most important one for a high-performance computing perspective, is this last row, the performance per watt, which is much higher for GPUs, because most high-performance computing facilities, they have a 50 megawatt line coming into their data center, and that's it. And if they want to maximize the amount of flops that they can get using that amount of power, then GPUs are the name of the game. And that's why all major supercomputers these days use GPUs. It's the best way to squeeze out the most floating point operations per second per watt. Okay, that was a lot of words about the difference between these two. So let's see. Maybe I'll try to show it here. I'll just go to YouTube. We're going to let Mythbusters explain the difference between CPUs and GPUs.
All right, I introduced to you Leonardo, and he's going to paint a picture for you guys in the way that a CPU might do it, as a series of discrete actions performed sequentially, one after the other. In 3, 2, 1. Let me speed it up. Ladies and gentlemen,
Leonardo 2.0.
When we hit this trigger on this thing, 2,100 gallons of air goes through these accumulators, out these valves, into all 1,100 of these tubes, into these tubes in which the bottom of is a paintball. Each of those paintballs will fly across 7 feet of space and in 80 milliseconds reach its target. Hopefully, when it's all said and done, it's going to paint the Mona Lisa.
GPU painting demonstration.
Yep.
In 10, 9,
8,
7, 6, 5, 4, 3, 2, 1.
Ladies and gentlemen, science class is now over. Thank you.
Okay, GPUs. Okay, so right, that just demonstrates that CPUs are these serial processors, which I kind of like how he cranked up the speed on the serial processor, because that's kind of what you can do with the CPU. And GPUs are these highly parallel processors. Okay, I already said that the most GPUs are made by NVIDIA, which publishes the CUDA platform for programming them. We're going to start by looking at the CuPy package published by NVIDIA, which is sort of a drop-in replacement for NumPy that runs on the GPU. So the name CuPy is a question.
I'm so sorry, and we can talk about this later, but will quantum computing make this less important in computing with efficiency and speed and everything? And you don't have to talk about this now. Anyway.
No, that's a great question. The answer is I don't know. Yeah, I don't know enough about quantum computing. My understanding is that the advantage of quantum computing is not that it's highly parallel, but that it can solve what's called NP-hard problems, meaning that problems that traditional non-quantum computing models cannot solve in polynomial time. The time to solve the problem is exponential in the problem size, and meaning it's not practical for any traditional computer to ever solve it. A lot of computer security is based on NP-hard problems, and quantum computing with this it lets you sidestep all these traditional computer science limitations because you're solving many different problems at once or something. I don't know. There's qubits involved. That's about all I know with quantum computing. But yeah, so I think it's a different approach to computing than the highly parallel advantage that GPUs give you. I think in the future you will see quantum coprocessors, much like we have graphics coprocessors. So the first, the adoption of quantum computing will first probably be offloading computations to an accelerator card, kind of like we're doing now with GPUs, but that's about all I know. Yeah. Okay, cool. Any other questions about what we've talked about so far? Cool. Let's talk about CuPy. So the name CuPy is supposed to make you think of NumPy, but with CUDA. And I just quoted the CuPy documentation here because it says it perfectly. CuPy is a NumPy, SciPy compatible array library for GPU accelerated computing with Python. And it acts as a drop-in replacement to run existing NumPy or SciPy code on NVIDIA CUDA or AMD ROCm platforms. And we're just using NVIDIA today. The documentation is pretty good, so I encourage you to take a look. But OK, let's see how it works. So traditionally, we import CuPy as CP, just like we import NumPy as NP. I'm going to run this, and because I'm connected to a T4 Colab instance, which I can confirm by looking at the top right where my mouse is, and it says T4, good, that's a GPU. And so when I run this cell, Colab has already installed CuPy for me, so nothing to do. Oops. OK, we can create a CuPy ND array, just like we can create a NumPy ND array. So these lines look really similar, but the first one I'm calling x underscore CPU equals np.array with numbers 1, 2, 3. And the next one I've just capitalized GPU in the name xGPU just because otherwise GPU and CPU look pretty similar. And this is saying cp.array, so I'm saying create a CuPy array. And when I do this, it actually creates an array on the GPU for me. And I can check this by running xGPU.device. And this is a special CuPy attribute, CuPy array attribute, that tells me where the array is living. So this says it's on CUDA device 0, so I know that the array is living in GPU memory, as opposed to the NumPy array, which always lives in CPU memory. And we can use the CuPy API, which mirrors the NumPy API, to perform operations on the GPU array that run on the GPU. So I can run cp.lineage.norm, just like NumPy has the lineage.norm that we used yesterday in the 2-point correlation function example. And so this computation ran on the GPU. We can also just do regular math, like multiply the array by 2. And this will also run on the GPU, and the result will actually stay on the GPU. And we can check, because I assigned the result to this xGPU2 array. So when I run xGPU2.device, double check, OK, good, it's still on the GPU. Of course, I said earlier that in order to see the results, it has to be sent to the CPU. So for printing purposes, when we print the array, it is fetching the result from the GPU to sort of magically display it for us. But we can also do that not magically. We can explicitly fetch the array from GPU memory into CPU memory with just the .get function. So I'm taking the GPU array, running .get, and I'm assigning it to this CPU to variable. And when I print this, it has the values we expect, 246. And if I print the type, we see it's a regular NumPy ND array, meaning it lives on the CPU, as NumPy arrays always do. OK, so we use .get to fetch arrays from the GPU. How do we send them to the GPU if we already have an array in CPU memory? We use cp.asArray. So cp.asArray, some CPU array. I'm using xCPU here. And then if I just call .device on that just to double check that it's living on the GPU, I get CUDA device 0. OK, great. OK, any questions about that? Using .get to fetch from the GPU and CuPy.asArray to send things to the GPU? Yes?
What happens if you accidentally mix the array types or try to? Will it fail?
Yeah.
Or?
Let's find out. Let's see what happens if we do xCPU times xGPU. Name error, because X GPU is capitalized. Get an unsupported a CuPy error, unsupported class type numpy.nd array. Yeah, it's not going to send it to the GPU for me automatically. But if I do cp.as array, I think this should work. Yeah. Okay, great question. Any other questions? Yes.
Does the as array call move the memory from the CPU to the GPU? Do you know, or does it create a copy?
Yes, good question. It creates a copy. Yeah, the CPU version is still there in CPU RAM, and it's also there now in GPU memory. Yeah, it's copied. Okay. Yes. Other question.
So I know JAX has a NumPy implementation as well. Is there any advantage to using CuPy over JAX's NumPy, or? I
think they should have similar speed. Yeah, I think you would use JAX if you wanted the just-in-time compilation capabilities and auto-diff, and you would use CuPy if you wanted something that was a drop-in replacement for NumPy, and you didn't need the JIT compilation or the computation graph or any of the algorithms that JAX has built in. I think CuPy is a little bit closer to directly programming the GPU than JAX is. JAX is more sort of layers of indirection. So it's a bit more of a complicated framework than CuPy. So I think if you only need CuPy stuff, then I would stick with CuPy. If you're doing something that needs some capability that only JAX has, then I would use JAX. Okay. Any other questions? Cool. Okay, so CuPy arrays can be used in a lot of places where you're using NumPy functions, thanks to NumPy's function and ufunc dispatch, which means that when you call a NumPy function, like for example on this first line, I'm calling np.lineage.norm, but I'm calling it on a GPU array. And NumPy is smart enough via this dispatch mechanism to look at the type of the argument, XGPU in this case, and see, okay, this is a CuPy array. I know about CuPy. CuPy has its own implementation that runs on the GPU of the linear algebra norm. So it's actually not using NumPy's implementation here, which is very confusing, but also makes it a lot easier to pass in a GPU array to your existing NumPy code. That's sort of the promise of CuPy, which works most of the time. But we'll see some examples where it doesn't. So despite the fact that we're using the NumPy function here, when we run this and check where the result is living, it's actually living on the GPU. So NumPy automatically dispatched the work to CuPy because it saw it was being called with a CuPy array. Okay. Now let's get into why we want to use the GPU, which is because it's fast. And as we time these functions, we're going to need to make sure that the GPU work is finished when we time the function, because otherwise we might be sending work to the GPU and saying, we're done, we sent the work to the GPU, but the GPU is still processing something. So we need the GPU to tell us, okay, I'm done, and that's how we can accurately time how long it's taking on the GPU. In other words, GPU work is asynchronous with respect to the CPU. But we can use this, we can get the current execution stream on the GPU and use stream.synchronize to make sure that the GPU work is done. So let's time something really simple, how long it takes to create an array of 100 million ones on the GPU versus on the CPU. I'm using cp.ones and np.ones. It takes 3 milliseconds on the GPU and 188 milliseconds on the CPU. This is for a couple reasons. One is that the GPU by default is using many CUDA cores. NumPy is kind of stuck using one CPU core. And traditionally, one CPU core cannot saturate the memory bandwidth. But also, even if you were saturating the memory bandwidth, the bandwidth on the GPU is so much higher than the CPU. And in case it wasn't clear, this problem of filling an array with ones is strictly memory bandwidth bound. So that's really the performance characteristic we're seeing. Other simple math operations, like multiplying an array by 2, are also memory bandwidth bound. So we should see extremely similar performance when we time the 2 on the GPU or the CPU. Okay. So yeah, GPU is many, many times faster. Any questions about that? Yes?
What is stream? Like stream synchronize?
Stream refers to a CUDA execution stream, which is a queue of operations that are queued up to run on the GPU. And that stream can run asynchronously with respect to CPU work. So things that might be on the stream include sending data to the GPU, executing a computation, which we call a kernel, as we'll see later, on the GPU, and fetching a result back. You queue those up on a CUDA stream, and then the GPU will execute them in sequence. And you can actually have multiple streams running on the same GPU to have multiple execution streams that can overlap work.
Okay.
Yes?
How many cores
On the CPU, yeah. Usually, this is a tricky one, but and sometimes it just takes some experimentation. But so first of all, CPUs, if you have a machine that has multiple CPU sockets, then you will definitely need at least as many cores as there are sockets. And you can check how many sockets your CPU has by running LSCPU, which is not available on Colab. Wow, that is a weird error message. That's fun. I will show it instead on my desktop. So I ran the LSCPU command. This is saying my desktop has 2 sockets, meaning there's 2 physical CPUs that have been plugged into 2 separate spots on the motherboard. And different sockets have different memory banks attached to them. And so you basically, and having 2 sockets doubles your total memory bandwidth. So you definitely at least need 1 CPU running on each socket. In detail, you probably need as many CPUs as there are memory controllers per CPU, which is not listed in LSCPU. It's probably something like 4 to 8 per CPU. So on my desktop with 2 sockets, I'll probably need like at least 8 cores to saturate the memory bandwidth. And yeah, it's a lot of times you just have to experiment with it and see where the bandwidth saturates. But it'll almost certainly saturate before you hit like all 24 CPUs or all the cores on a CPU. Yeah. That. Okay. Any other questions? Yes.
So you showed some examples like from CPU to GPU, like you can multiply and check it, and I think in the next stranger also. Like, is it better to work only in GPU or only in CPU, or mix like from CPU to GPU and vice versa is good, like in the code?
Wait, sorry. Can you repeat the question?
Like you showed, like from CPU to GPU, some codes or some calculations.
Yeah.
So the calculations, is it better like to work only in GPU if I am working in GPU, or if I am working in CPU, I should continue the calculation in CPU?
Yeah, that's exactly what we're going to talk about now. And the answer is there needs to be enough work to justify sending the data to the GPU.
Okay.
Yeah, and we'll unpack that over the next couple of minutes. Okay. Yeah, so we saw that the GPU is really fast. It filled that array of ones in just a couple of milliseconds. And likewise, it multiplied this array by 2 in just a couple of milliseconds, whereas the CPU took over 200 milliseconds. So is it worth sending the array to the GPU just to multiply it by 2? And we can answer that question by timing it. Let's look at this. So I think this may be the first time we're using what are called cell magics instead of line magics. So this time it command that I've highlighted with the 2% signs, that runs the entire cell and not just the line and times the execution. And also the statement that's on the same line as the time it command is a setup statement. So we're not actually timing how long it takes to create this array of ones on the CPU, but we're just sort of creating it as a preamble to the timing. Then we're using cp.asArray, which we saw sends the data from the CPU to the GPU, or copies it to the GPU, I should say, multiplies it by 2 on the GPU, and then we fetch the result back and we synchronize just to be sure it's all done. And we see that it took 500 milliseconds as opposed to just staying on the CPU took 80 milliseconds. So, yes, question?
So if you initialize with CP, then you're not creating it on CPU and then transferring it to GPU. You're initializing in GPU, right?
Yeah.
Okay, my question is, how does this interact with, say, something like PyTorch, where a lot of bottlenecks can show up because your algorithm, your machine learning algorithm or your parameters are on the GPU, and then when you want to run something through them, you have to define your GPU device and then move your array to a GPU device. Can you initialize it with CP and then use it with PyTorch?
I think so. There's there's a CUDA. There's all these GPU arrays implement a standard interface. It's called DLPack that lets different libraries and their different array implementations talk to each other. So it's supposed to work that if you allocate an array with CuPy and pass it to PyTorch, it'll stay on the GPU and you'll never incur this performance cost of getting back to the CPU.
Related question. This might be, I think this is very naive, but can you load data with CP?
It's not a naive question. Like load data from disk, right? Yeah. I don't know. The short answer is if I were to do this here, it would load it through the CPU. I'm pretty sure about that. There are some technologies that NVIDIA is developing. I think one of them is called GPU Direct. That might be a different GPU technology. There's a lot of similar sounding ones, but the idea is that because sending getting data from the drive to the GPU currently has to go through the CPU, and what if we could eliminate that and send it directly to the GPU? So that there are technologies that are being worked on to implement that. I'm almost positive that this is not present in Colab, and it's not on my desktop either. I think it needs what's called RDMA support, where it's like remote direct memory access from the file system or the drive to the GPU. So it needs hardware support and kernel firmware support, and it's a complicated software stack. But it is a bottleneck, especially for machine learning training on a gazillion tiny files. So yeah, it'll become more standardized in the future. Mm-hmm. Okay. Any other questions about that? Okay. Right, so sending the data to the GPU just to multiply by 2 was totally not worth it. In order for it to be worth it, for us to use the GPU, the data needs to either originate on the GPU, creating some array with CP, or we need to be doing a lot of math on the GPU for it to be worth it. Another way to say that is we need a high compute density on the GPU. Compute density, formally, you could define it as the number of flops, the number of floating point operations being done per byte of data that we send. And we want that to be really high. Matrix multiplication is a good example of that, as is machine learning training, where you get some data on the GPU and then you iterate on it a bunch of times. Or expensive trig functions. And we'll see some examples of all of that. But here's just a quick example of sort of the classic problem that GPUs are really, really good at, which is matrix multiplication. So here I'm creating a 10,000 by 10,000 floating point array of random numbers on the CPU, and then sending it to the GPU, doing the matrix multiplication with this @ symbol, and fetching the result back. It took 800 milliseconds, including sending and getting the data back to the GPU. But yeah, if I remember correctly, like matrix multiplication does something. It's like the amount of math is cubic in the number of in the matrix size, so it's like 10,000 cubed operations or something like that. But it's very compute dense. Is the point. There's a lot of math that has to be done when you send it to the GPU, which is great. Because if we run on the CPU, hopefully this won't take too long, but it'll probably, it should be around like 14 seconds execution, because it's or at least when I ran this notebook on my desktop, it took 2 seconds. Colab has very wimpy CPUs, which actually I can, while this is running, I can tell you if anybody wants to tackle a problem that uses numba parallelism or any of those tools that we used from yesterday, and you don't have, and you're not set up to run on your laptop, I did set up binder instances, which are linked from the repo, and hopefully, if you click on that link and sign in with any Google account, then you should be able to launch a Jupyter Lab session that's running at Flatiron Institute, which is where I work, which has the whole repo, and you can open any notebook and run it, and you'll have more CPU cores than you'll have in Colab, and probably about as many as you have on your laptop. And there's also a link for a GPU-enabled binder, if for some reason Colab isn't doing it for you. Okay, so yeah, feel free to use that for the hack sessions or for running these notebooks. Okay, the CPU version is still going.
Hello.
Yes, question.
So earlier you showed the multiplication by 2 in 2 places, but the time showed differently. I think here you mentioned X CPU times 2, and earlier also you showed it, but the times were different.
Yeah, that is a great point. I think the reason is that this one is an out-of-place multiplication, and this one is an in-place multiplication. And out-of-place is more expensive. It involves dynamic memory allocation and writing to fresh memory, which usually incurs what's called a first touch allocation, where when you start writing to a new page of memory, it has to wipe it with a bunch of zeros, and it's really expensive. Okay. Whereas this is reusing existing memory.
Thank you.
Yeah. Okay, that took 19 seconds on this poor Colab CPU, and 800 milliseconds on the GPU. And okay, because data transfer is really slow, as we saw, and knowing the location of your data is so important, CuPy will not automatically copy data back and forth. It'll instead throw an exception, like if we allocate something on the GPU and then try to use it in a way that requires copying to the CPU, it's not going to work. CuPy requires you to use .get, just so you as the programmer are explicit with your intentions to copy the data and incur this performance cost. Yes?
But wouldn't it be inefficient to use a GPU for CPU calculations? Like, for example, sometimes when you use parallelism and you use it in a stupid way, it can make your calculation slower rather than accelerated.
Yeah. So what was the question?
Yeah. So
I agree with what you said, but sorry, I missed the question.
yeah, I guess I'm like, are there like any calculations that are like more efficient more efficient to use on CPU?
Yeah.
Something like maybe simple than rather than like using GPU.
Yeah. If you're not doing like NumPy things, I think most things you would do with CuPy are going to be pretty efficient on the GPU, as long as you have enough work to justify sending the data, or you can originate the data on the GPU. As I think we'll get into more examples with Numba in the next section, where in theory you could write code that has, for example, a lot of if statements, a lot of like branching conditionals that would be bad on the GPU because of this idea that you have to run sets of cores in lockstep on the GPU. And so if each core is making its own decision and going down its own code path, that's going to be horribly inefficient on the GPU. But CuPy is not really going to let you write that kind of code. Numba CUDA definitely does. Yeah, so does that answer your question? Okay, cool. Let's see, how are we doing on time? It's 9:45, and I think our schedule is to go until 10, and then take a break, and then do the problem set. Cool. Okay, let's press on into Numba CUDA. So using CuPy abstracts away a lot of the details of programming for the GPU, but I just wanted to give you all a little bit of taste of what it looks like to program the GPU directly and interact with the threads and the CUDA compute model. Okay, and we're going to use Numba, which we used yesterday for the CPU, but today we're going to use it on the GPU. So programming the GPU requires writing a special function called a kernel. And the GPU executes many copies of this kernel in parallel and in what's called a grid. And the grid is made up of thread blocks. Each block contains many threads, and all the threads are executing the kernel. The kernel also can't return anything. It has to modify array arguments that are passed in. So in short, CUDA kernels are how we run programs on the GPU, and they execute as a grid of thread blocks. So I find that phrase useful to remember. It's a grid of thread blocks, which also the illustration is missing here. So I will show it in my notebook. So this is illustrating the GPU compute model, where you have these blocks of threads that are working together as a team and all executing the same operation, just maybe on a different piece of data. So for example, the first thread in this block might be operating on the index 0 element of an array. The second thread might be operating on the index 1 element. And they're all doing the same operation, just on a different piece of data. Okay, let's make this more concrete by actually writing a kernel in CUDA. We're going to implement a calculation to increment every element of an input array by 1 on the GPU. And this is how we write it in Numba. So yesterday we used numba.jit. Today we're using numba.cuda.jit. Here I've imported CUDA from Numba, so it's just called cuda.jit. And so remember, every thread is executing this entire function. So we need to know our thread ID, so we know which element of the array to operate on. And we do that by using these special variables, cuda.threadIDX and cuda.blockIDX. So we can think of this as sort of a 2D array where the thread is the fastest dimension, it's the innermost dimension. The block ID is the outer dimension, and the block width is the number of threads. So this is, it's block width, it's the number of threads across a single block. So the flattened index for this array is t, the fast dimension, plus the block ID times the block width. This is indexing a 2D array, except the 2D array is the number thread grid. Sorry, the CUDA thread grid. And then we just do a check to make sure we haven't run off the end of the array, because the block size may not be commensurate with the array size. And if we are within the array size, then we increment the array by 1. So what we've done here is assigned every thread to a different element of the array on the GPU. That's what all this complicated math was doing. And then we're just incrementing, having that thread increment that array by 1. Okay. Another way to see this is that, or think about this, is that this is as if we're writing a for loop over all the elements of the array in Python, except we're not writing the loop itself, we're just writing the body of the loop. CUDA is executing our function this way. So for each block in the number of blocks, and for each thread within the block, so this doubly nested for loop, execute this function calling with the thread index and the block index, which lets us do the math that we did to compute the index in the global array. We're not actually, we don't actually get these variables as arguments. They're passed in via the special CUDA.threadIDX and CUDA.blockIDX. Okay, so we're not writing the for loop part, we're just writing the body of the loop. This is what I just said. And we need to set some values of the number of threads per block and the number of blocks. And I have set them for you here. It's mostly a performance tuning parameter. We're going to do 32 threads per block and then just enough blocks to cover the whole array. And that's all this math is doing. So I set up an array of 100 elements, a very small array by GPU standards, and then just 32 threads per block, and then it's going to be like 4 blocks because it's a small array. And then we call our increment by 1 kernel just with the number of blocks and threads per block, passing in the array on the GPU, synchronize, which we saw before, and then print the result. And if everything goes well, which I forgot to run this guy, then our array of 1s should now become an array of 2s. Okay. Yes, question?
This seems a bit arbitrary. Like, can you encounter a situation where your array is so large that you can't assign each element to a thread? Or
yes, it can happen. But the number of blocks that you can launch is actually really, really big. I think it's like a 32-bit limit, so it's like 2 billion blocks. And you can actually have like 1024 or 2048 threads per block. So you can process really big arrays with a single kernel launch. If you were to exceed that limit, which could totally happen, then you could you could have each kernel loop over a number of elements. Like here, the kernel processed a single element, but you can have a kernel loop over multiple elements. So that's how you would deal with that. But yeah, all the blocks may not be executing at once. There's usually a couple of dozen of SMs or compute units on the GPU that can be executing, and they each execute a block or a couple of blocks. But then other blocks are waiting to be executed on the GPU, and it just handles all that. Cool. So I know that was a lot, and just a lot of new concepts to throw at you, but I just wanted to sort of give you a taste of what it looks like to program the GPU directly. Okay. Also, I'm going to show you a shortcut that I encourage you to use in the problem set, which is CUDA.grid. So now I rewrote the function that we just wrote using much simpler indexing math. I'm using the shortcut that NumberCUDA gives us, which is this CUDA.grid function, which automatically looks at the launch configuration, the number of threads per block, and the total number of blocks, and computes a global thread ID. And the variable 1 here just says we're doing this as a one-dimensional array. And this part is the same. Increment the array by 1. I don't even think I ran it, but let's do that now. OK, increment by 1. And then this is actually going to be n threads and, oops, what I call it? No, threads per block and n blocks. And it's n blocks, threads per block are, and I think this might actually give us 3 now, because the array is probably 2. Let's check. The array is 2, so how do I delete things? OK, so I just ran that. Cool. OK, so now it's 3. So this new function worked just like our old function, except the math is much shorter, and I encourage you to use this shortcut in the problem set. OK, questions? Yes?
So how do you decide on how many threads to use?
It's mostly a performance tuning parameter, and the amount of threads determines the number of blocks that can run on a single compute unit at once. And for this application, it doesn't really matter what number of threads per block we use, because we're not using shared memory or a lot of registers or any other precious GPU resource that would limit the number of blocks we can have on a GPU, on a compute unit. But yeah, you're trying to balance the number of threads with other resources that the kernel is using, which we haven't even talked about, but mostly shared memory and registers. Yeah. So there are multiple things that can limit the number of blocks that can execute on a compute unit, and you're trying to keep them all in balance. But for today, I've just given you the values both in here and in the problem set of the number of threads you should use. Yes, question?
How does this extend to multiple GPUs?
I have never used NumbaCUDA for multiple GPUs. I think it probably. So the answer is that it's manual on the part of the programmer. If you're programming at this level, it's manual. You have to get a stream on another GPU and submit it to the stream. I've never done that with Numba, but I'm sure they have a way to do that. With CuPy, I think they have some built-in facilities to automatically send things to multiple GPUs. But once you get down to this level where you're writing kernels yourself, then you, the programmer, have to get the different streams and manage the different GPUs. But yeah, the short answer is use different streams. OK, we're about at time for our break. So is there any last question about CUDA before we go to break? Cool. If this is sort of whet your appetite, I linked a good tutorial here, because most CUDA tutorials online assume some C++ knowledge, because that's sort of the native language of CUDA. This one does not. I really like it. So check it out if you're interested in learning more. OK, thanks for your attention. OK, let's go ahead and get started with the problem set so that we can end on time, or maybe a little bit early and get to lunch. OK, so the problem set also requires a GPU, so I recommend that you run it in Colab. The link to open the notebook in Colab is in the repo. It's the last Colab link in the table. Should pop open this notebook, problem set X. And just like before, when this notebook opens, you're going to need to go to the top right next to the Connect button, click the little down arrow and select Change Runtime Type. And when you do that, you should be able to select a T4 GPU and hit Save. And then you can press Connect in the top right, and it should start a GPU Colab instance. And yeah, if you see in the bottom, it says Google Compute Engine Backend GPU, or it says T4 in the top right, then you should be all set. Okay, so we're actually going to revisit the same problems that we looked at yesterday, like the computing the value of pi with Monte Carlo, or computing RA and DEC coordinates with RA and DEC coordinates, this time with CuPy, and also a correlation function, mostly with CuPy, and then a little bit of numba at the end. So please get started with this notebook, and I'll walk around, see how people are doing, and I'll show my solutions as we go along, just like yesterday. Okay, I think a number of you have already figured out the how to implement the first function in CuPy. So let me show that with the notebook. And it's if you're wondering if your solution was too simple, that probably means that you got the right solution, which is just to copy and paste the function and change the NPs to CPs. And in fact, I think you just have to change this first NP to CP and leave everything else as NP because of the NumPy function dispatch I was talking about. So this should run entirely on the GPU because this generates a GPU array and everything else operates on the GPU as a result. Oh, runtime disconnected, that's fun. I wonder did it survive? Yes, I think it survived. Okay, okay, the CPU version took 20 milliseconds. I wrote here it should be 10 times faster on the GPU. That number comes from my desktop. Yeah, okay, so it's only, in this case, it was only a couple times faster. That I am now curious. Let me run this one more time, and I'm now curious if I change these NPs to CPs. 2 milliseconds, okay. All right, so these GPUs and CPUs are shared resources on Google Colab. So the timing, yeah, you may need to time these a couple of times to get and see if there's some variance in the results. But in this case, yeah, it was about 10 times faster, just with this, this one line change of NP to CP. All right, I'll let you keep working on the next part. Okay, I think people are making good progress, so I'm going to show you my solution for this, the CuPy RA DEC calculation, which I am pretty sure is pretty simple because as I've hinted to you here, you can just use the NumPy function as is, as long as you pass it CuPy array arguments. Because NumPy will look at the argument types and see that they're CuPy arrays and dispatch the actual computation to CuPy, which runs on the GPU. Okay, so we need to do, I will call this RA GPU equals cp.as array. Catalog, RA, and I'm so used to having Copilot autocomplete these lines, but I gotta do DEC GPU. I think maybe these guys have to be CUDA also, but let's try this first. All right, and I'm just going to turn off the timing statement just so we can run it, see if it runtime disconnected. Did it? Oops, I did not run this cell. And I did not run this cell. Sorry about that. Okay, so this is timing the CPU version with NumPy. $1.5 Let's see if the GPU version is right. Okay, it ran. Let's time it. Okay, 73 milliseconds. Great. Much faster than 1.5 seconds. Yeah, so that's it. All I did was send the arrays to the GPU, and then I called the exact same function with the CUDA array arguments. All right, I'll let you keep working on the next part. Okay, I'm going to show my answer now for the CuPy two-point correlation function problem. So the NumPy implementation is provided for you here. There's nothing for you to fill in. This is basically the same code from yesterday that did the big array broadcasting thing where this line here formed an n by 3 array. And we're going to see if this is kind of a brute force. It's poor memory usage, but we're going to see if CuPy can speed it up for us. Okay, so I will run this because I keep forgetting to do that. Okay, so you may have discovered that if I do something like pause GPU equals, actually let's do a GPU RNG equals cp.random.default RNG. Can't remember if I already made this, so I'll do it again. GPU dot uniform 0L. We'll just do a small problem 50, 3. And now, in the last problem, we saw that we were able to call the NumPy function directly unmodified. And because we are passing a GPU array, NumPy dispatched all the functions to the GPU using CuPy. But here we see it doesn't work, and it fails in the numpy.histogram function. I don't actually know why. For some reason, NumPy does not dispatch this function to CuPy, maybe because it's considered a high-level function, that implements some histogramming algorithm, and so it's not qualified for dispatch. But in any case, so CuPy does implement the histogram function. So let's copy the body of this function and put it in our new CuPy function. Yes?
I think it does because mine worked, but histogram edges is not CP.
Oh, so it works if you do cp.linspace?
Yeah.
Oh, cool. Yeah, and fix the dot flat. Awesome. Okay, that's funny because if it can dispatch on on the main argument to histogram, I don't know why it wouldn't just convert the. Yeah. Okay. Cool. Thank you for letting me know. Let's try that. So this will be cp.linspace, and I'm going to copy this. I guess I actually already set up the. Oh, right, because I think we want, right, because actually, yeah, I forgot. For this, we do want to consider the time it takes to send the data to the GPU and get it from the GPU. So we'll do pause GPU equals cp.as array, pause 0.1. I think these were the arguments. Okay, I'm going to run this without the timing just to see if I pause. Oh, right, yes, because I hate that. It's hidden up there in the. Okay, so if you've tried this problem, you may have run into this error. The numpy.flat iter object has no attribute dtype, and this happens when we call a histogram on this dij.flat. And for some reason, this works in NumPy. It doesn't work in CuPy. when you do dot flat, it gives you this flat iter object, which is a 1D view on the NumPy array. And most of the time in NumPy, it's equivalent to just reshaping to a 1D array. But every once in a while, it's not, and this is one of those cases. So the fix is to just sort of express the same idea of reshaping to a 1D array by calling dij.reshape with -1 as the argument to the reshape function. You may have also seen dij.flatten used in similar context, but just be aware that this creates a copy of the array, so it's just not good for performance. Okay, so I replaced the flat with the reshape. Now I should be able to run this. Value error, x must be a CuPy array. Let's see. And pause GPU. That's right. I called the CuPy function with the NumPy array. Okay, that ran. So now I will time it. That took 1 millisecond. The NumPy version took 378 microseconds, so it was 3 times faster. But what happens if I run the same thing? But with 1,000 points. First, let's check how long the NumPy version took. It was 149 milliseconds. And this one took 20 milliseconds. So the point here is that once we have a big enough problem for the GPU, once we're doing the 2-point correlation function on 1,000 points instead of 50 points, it's worth it to send the data to the GPU and do the computing there and get the result back. But for a very small problem, it's not worth it. And there's some questions. Yes, over there.
So when we are defining the 2-point correlation function in GPU, why you didn't change where you define the NumPy histogram or line space or NumPy random integer? Why you particularly change only the histogram, I think?
So just to make sure I understand the question, is it why did I only change this line and not this line?
Not this line, and also the square root and the random integer?
Yeah. And the reason is for some quirk of CuPy, which has just been pointed out to me. NumPy, a quirk of NumPy or CuPy, I'm not sure which one. NumPy will not successfully dispatch this function to CuPy if the bins argument is not already on the GPU.
Okay, and for other cases, it's not a problem, right? So how would I know that which function I have to define in CuPy and which function I will keep it in NumPy?
Yeah, because it'll give you an error message if you get it wrong. Yeah, because it's pretty good about not automatically transferring data back and forth between the CPU and GPU because that's expensive. So it wants you, the programmer, to know about it. So it'll give you an error message instead of silently doing a bad thing.
Okay, thank you.
Yeah. Okay, in the back.
Is this the kind of thing that would be good to check if you have the same answer as... Because I did check, and it's definitely possible I implemented something wrong, but I was getting different answers between the two.
Cool, yeah, let's go ahead and check that now. Let's use the 50 particle version. There is one potential gotcha here, which is if you're using different input data sets, which the way this is written, it could be easy to do. So I will reinitialize the RNG here. Get 50 points, send it to the GPU, compute the result, and I think I have to do this now for NumPy. Let's go back up to our NumPy version. So I'm going to reinitialize the RNG to ensure we have the same data points. Really, I should just be using the same data points, but actually I think if I do this now, it'll be safe. Okay, so I have NumPy res and res. Let's just look at it. Okay, that's it's a funny looking correlation function. It's probably right though because this is only 50 data points. Yeah. Okay, that looks really similar. Usually you're not supposed to use double equals, because one of them is false, but I bet if we do. The reason you're not supposed to use double equals is because floating point math is not associative or commutative in some cases. So the all close function allows a little bit of tolerance in floating point comparisons. And when we do that, we find that they're all close. So I think, yeah, probably if you're getting the different result, just double check your implementation, but also check that you're actually using the same input data points. Yeah, I was being a little lax about that, this notebook. Yes?
I just want to say that something I realized, which is kind of cool, is that you can template these functions. So if you add, say, the module as another parameter and call it like XP, then you can just generalize it on any runtime that you're using. So you don't have to rewrite these functions for each
Yes,
architecture.
Thank you. Yeah, that's a great point that I did not talk about at all. But if I think there's even, let's see, I probably missed a couple. Maybe that's it. So if I make XP an argument to this function, then I could call, I'll just call this XP, compute two-point correlation function. I could call XP compute two-point correlation function pos, and then, pass NumPy as the last argument, or CP if this is a GPU array, or I think there's even a helper function. Maybe you're using this. I forget exactly what it is, but it's like kupy.get array module, I think. Can we look at a doc string? Thank you. Okay. So kupy.get array module returns either NumPy or kupy, depending on the type of the argument. So so another way to do all this, rather than taking an XP argument, is to hide the XP initialization inside the function and do kupy.getArrayModule pos. So then whatever array type is passed into this function, it'll automatically switch between libraries. Yeah, it's a great point. Thank you. Yes?
Yesterday we used like number and now like kupy. So both will give us like the running time is same, the computation time for number and kupy. Like if you
for simple operations, absolutely. It's just going to be more work probably to do the number version, and you'll also incur the just-in-time compilation cost the first time you run the function in number. So when you can use kupy, if you're just like replacing a bunch of NumPy math with kupy math, then I think kupy is easier than number.
Okay.
But when you want to implement something that's not array-oriented, and I think the example further down is the Monte Carlo pi example, which is not really an array-oriented problem, that's when number really shines.
Oh, thank you.
Okay, I will let you keep working on interpreting the results and the last part, which is the number CUDA Monte Carlo. And I think at this rate we will get to lunch a little bit early, but I'll let you all work on this for a little while. So I think some people might be losing their Colab GPUs, maybe because we're all connecting from the same location, and I'm not sure why, but Google Colab GPUs are not a guaranteed resource, but there is a backup, which is if you go back to the GitHub page, so this is the L. Garrison GitHub repository, and look at option 2, Flatiron Institute Binder Hub, and click on the GPU-enabled binder. That should launch a Jupyter Lab session that has a GPU. If you can keep using Colab, please do, because we can only support like 28 users on this Flatiron Institute GPU, so like half of you. So if half can keep using Colab, that would be ideal. I think Google Colab is either angry at us or is down in general. Let's see, Google Colab service status. I don't know. I'm seeing a lot of green check marks. So maybe we're just connecting. Yeah. Maybe it's just us. But that's okay. We're sort of at the end of the session. I'm going to, yes, I have a running server. I'm going to show you my answer for the last part in Binder instead of Colab. Let's take a look. Okay, I'm going to start up here. Hopefully I don't need this stuff. Might need CuPy stream. I must have started a CPU binder. Sorry, give me 1 second. Okay, great. We have a CUDA-enabled binder, and we looked at the answers to everything else, except the Numba CUDA stuff where you're writing your own kernel. So let me show you the answer to that. So in this one, we are, just like we did on the CPU, we're generating a pair of XY points using this very specific syntax that I've given you. And each thread, I told you, should use do n iterations just to give it enough work to be worth doing on the GPU. I don't even know if we need the iteration variable. So I'm going to call it underscore for underscore in range n iter. We're going to generate an xy point, and we're going to say if x squared plus y squared is less than 1, n circle plus equals 1. And we're going to write this thread result into exactly where I told you, an output array that's already been allocated of length, the number of threads, just because that's not the highest performance way to do it, but that's the most convenient, and I think it's not going to matter in the end for performance. So fingers crossed, if I run this with 10,000 iterations per thread and the configuration I gave you, that should run, what is that, 64 million samples. Let's run it once, so without the time it statement. Oop, we got to do, oh no. I'm going to hope this will let me keep running, okay. I think it's blocks, comma, threads per block. And just call that with what arguments RNG states, n iter, and the output array where each thread writes its count. And then I've already given you how you compute pi from that, which is to just sum the results across all threads with out.sum. That'll happen on the GPU. And we'll also print pi down at the bottom here. And we got a warning that this problem is too small for the GPU to really be fast. That's OK. We got the right answer. And for fun, we will time it on the, right. We're going to time the native number CUDA version, which is not doing any temporary array allocations. Takes 3.8 milliseconds. And then we're going to time our previous CuPy version, which I did not implement here. So I am going to copy out of the solutions. PyPy. And we're back here. Okay. Am I missing any variables? Let's find out. Let's run it once without time it. Okay. It is compiling. Come on. You can do it. CuPy is doing some warm-up step because this is a fresh binder environment. Okay, that's done. So now we'll time the CuPy version. 40 milliseconds, so more than 10 times slower than the native Numba CUDA kernel we wrote. I mean, it was a lot more work to write this Numba CUDA kernel. Some funny syntax in here. You have to worry about threads and blocks and so on. But I hope this gives you a little taste of the performance potential from writing your own CUDA kernels. And I hope you've learned that you can actually write kernels without ever leaving Python. And I think we'll end there. I pitched my own project idea for you all at the bottom here, which is if you wanted to write a Numba CUDA version of the two-point correlation function, that could be really, really fast, and that sounds fun. I haven't done that myself, but it could be a cool project. So I think we're going to leave it there. Thank you all for your attention and participation.